Good evening everyone, I am Shivani Dhok and I welcome you all for the 7th week tutorial of this course, that is Principles of Signals and Systems, and the topic that was covered in this week was Fourier Transform, and I would be covering the questions and some concepts related to same topic. So to begin with, let's start with the recap. Let's start with the recap of the content that was covered in the 7th week. So basically this 7th week started with the definition of Fourier transform. So this 7th week started with the definition of Fourier transform and Fourier transform for continuous time signals. Therefore for any signal, let's say x of t, its Fourier transform is given as x of omega, which is equal to integral from minus infinity to infinity x of t e power minus j omega t dt. This is the Fourier transform, and this is Fourier transform, and we can get back x of t with the help of this x of omega using inverse Fourier transform definition, which is given by the formula as x of t is equal to 1 over 2 pi integral from minus infinity to infinity x of omega into e power j omega t dt. And it was said that this xt and x of omega, they form a Fourier transform pair. So they form a Fourier transform pair. Now after looking at them, next Dirichlet's conditions were analyzed. The first Dirichlet's condition is that, so basically these are necessary conditions and not sufficient. So it said that it is absolutely, if a signal x of t is absolutely integrable, that is, if we have integral from minus infinity to infinity mod of xt dt less than infinity, then the Fourier transform of that signal exists. Otherwise, it does not exist. Next is that it has a finite number of maxima and minima in any finite intervals. And next, the third condition is it has finite number of finite discontinuities. After looking at this, the next thing that was discussed was its relation with Laplace transform. So we know that the Laplace transform for any signal is x of s is equal to integral from minus infinity to infinity xt into e power minus sigma, or let's say minus st dt, and this sigma, this s is basically a complex frequency which is given as sigma plus j omega. So this we can write as integral from minus infinity to infinity x of t into e power minus sigma t into e power minus j omega t dt. So if we compare this definition here and this definition here, it can be clearly seen that this x of s is basically Fourier transform. This is Fourier transform of xt into e power minus sigma t, and the Laplace transform is equal to Fourier transform when my sigma is equal to 0. That is, this x of s at sigma equal to 0 is equal to my x of j omega only when this sigma equal to 0 line is in ROC. So this j omega axis should belong to region of convergence. In that case only this definition is valid. After that, the properties of Fourier transform were discussed, and the first property that was discussed was the linearity property. Next, the time shift property was discussed. So let us just revise these properties one by one once. So the first property that was discussed was this linearity property. So it said that if x1 of t has Fourier transform as x1 of omega and x2 of t has Fourier transform x2 of omega, then linearity property says that a x1 of t plus b x2 of t has Fourier transform as a x1 of omega plus b times x2 of omega. Similarly, the time shift property says that if I have a shifted version of a signal, that is x of t minus t naught, then the Fourier transform of this is e power minus j omega t naught x of omega. Then the third one is dual of this, which says that if I multiply in time domain by some complex exponential, which is something like this, then we will get a shift in frequency domain, something like this. This is frequency shifting property. So for ease, let me just put some arrows here. The next property that we looked at was time scaling property. So it said that if I consider the Fourier transform of x of at, where a is some positive constant, then the Fourier transform of this is simply 1 over a x of omega by a. After that, next the time reversal property was seen. So it says that if I flip a signal with respect to time axis, in that case the Fourier transform also gets flipped. The next property is an important property and is useful in many cases, and that is known as the duality property. So it says that, so this duality property, it says that if x of t has a Fourier transform x of omega, that is capital X of omega, and suppose now this function, this has, instead of omega, instead of in frequency domain, we consider capital X of t, then this will have a Fourier transform of 2 pi x of minus omega, where this x is the small x, that is this function here. This is an important property which many times simplify the situation for us. The next property that was looked at was this differentiation in time. So it says that if I consider the differentiation of input signal, that is d dt of x of t, then in that case the Fourier transform is simply j omega x of omega. Similarly, this differentiation in frequency domain says that minus jt xt has a Fourier transform of d omega of x of omega. The next property that was looked at was this convolution in time. So it says that if I have input, or if I have a signal which is basically convolution of two signals, then this will have a Fourier transform as simply multiplication of these two signals, that is x1 of omega into x2 of omega. And the dual of this is, if I have multiplication in time, then I'll get a convolution in if I have multiplication in time, I'll get convolution in frequency domain. That is, if I have x1t multiplied by x2t, then in that case I'll have its Fourier transform as 1 over 2 pi x1 of omega convolved with x2 of omega. These were the properties that were covered, and after that an important property was covered which was related to the energy of a signal, and it said that this Parseval's relation, it says that integral from minus infinity to infinity mod xt square dt is equal to 1 over 2 pi integral minus infinity to infinity mod of x of omega square d omega, and this is known as Parseval's relation or Parseval's theorem, and it actually gives a very good relation between the energy in frequency domain and energy in time domain. It basically says that the energy, if you change from one domain to another domain, the energy does not change. So this is the basic thing of this Parseval's relation, and we'll see that how this helps in analyzing the signals in some examples. The other thing that was covered was this autocorrelation function. So this autocorrelation is basically given as minus infinity to infinity autocorrelation of a signal, say x of t. So it is given as x of t plus tau into x conjugate of tau d tau, and this is represented as rxx of t. This is known as autocorrelation function, and its Fourier transform is sxx of omega, which is simply mod x omega square, and this thing is known as the energy spectral density, that is EST. And when I integrate this energy spectral density over this entire range of omega, in that case I'll get the energy of that signal over that particular band. After that, the concept of Fourier transform for LTI systems were analyzed. This is basically a simple extension of this convolution property of Fourier transform. So it says that if I have an LTI system, let's say with impulse response ht, and I give an input xt, then its output is y of t, which is simply convolution of xt with ht, and y of omega will be equal to x of omega into h of omega, and this h of omega is equal to y of omega upon x of omega, and this is known as the transfer function of your LTI system. This is similar to what we have with Laplace transform. So this is also same thing, and it is nothing but convolution property resulting into multiplication in frequency domain, and the transfer function is simply the frequency domain representation or Fourier transform of output upon Fourier transform of input. And another thing that was discussed was this differential equation based characterization of LTI systems. After that, low pass filters, like ideal filters, were designed or discussed. So the first one that was discussed was low pass filter. So it says that it will allow only frequencies which are less than some cutoff frequency to pass through it. The high pass filter says that it will only allow a set of frequencies which is higher than some cutoff frequency. Band pass filter says that it will only allow a particular band of frequencies, let's say from omega 1 to omega 2, to pass through it, and other will be restricted, or it will be just made to 0. The next thing that was discussed was this band stop filter. It says that I'll restrict the signal, or I'll not allow a signal in a particular frequency domain, particular frequency range, and whereas allow all the other frequencies. The next thing that was discussed was 3 dB bandwidth. So this 3 dB bandwidth or 3 dB cutoff frequency, 3 dB thing, let's say omega 3 dB, it is the frequency at which this mod of h omega square is half of its maximum value. And the same definition can be extended for the bandwidth of a signal, and a band limited signal is a signal, which is the next notion that was covered, that it is non-zero only for a particular band, let's say from minus b by 2 to b by 2, and after that it is 0. So this is a band limited signal. So these were the concepts that were covered in this week. Now let us start with solving some examples of this Fourier transform. So let us look at the very first question. So the very first question says that we need to find the Fourier transform of the signal xt is equal to e power xt is equal to e power minus at into ut. So what do we have here is this signal, and we need to find the Fourier transform of this signal, and we have been given this, that is this a is greater than 0. So if this a is greater than 0, then the Fourier transform exists. So let us try to find it out. So let us look at this. So we have this Fourier transform x of omega is equal to integral from minus infinity to infinity. Let me simply partition this in two parts for simplicity afterwards. And x of omega is equal to minus infinity to infinity xt e power minus j omega t dt. So this is equal to integral. Since we have this unit step function, this will be non-zero only when your t is greater than or equal to 0. So we can write this integral as 0 to infinity. X of t will take value as e power minus at into e power minus j omega t dt. This we can write as 0 to infinity e power minus a plus j omega t dt, which is equal to 1 upon minus a plus j omega into e power minus a plus j omega t, and this will be varying from 0 to infinity. Now this function, this exponent will tend to infinity, will tend to 0 when t is tending to infinity only when this a is greater than 0, and we have been given that condition here. So based on this condition of a greater than 0, we can say that as t tends to infinity, this exponent tends to 0, and therefore this x of omega is equal to 0 minus 1 upon minus a plus j omega, which is equal to 1 upon a plus j omega. So this is the Fourier transform of the signal which is given here, that is xt equal to e power minus at ut. Now let us look at another signal which is something similar, but now the condition that we have is that this a is less than 0. We can go ahead and solve it in similar fashion and argue here that since a is less than 0, that is, since a is negative, this exponent will tend to 0 and this won't converge. But instead of doing that, let us do this by checking out the first Dirichlet's condition of absolute summability or absolute integrability. So what we will check is xt is equal to e power minus at ut for a less than 0 absolutely integrable. So let's check that. So what we will do is we will consider minus infinity to infinity mod xt dt. This is equal to integral from 0 to infinity mod of e power minus at dt, which is equal to integral 0 to infinity e power minus at dt. Since this exponent function will always be positive, so we can just remove this mod sign, and this we can write as e power minus at upon minus a from 0 to infinity, and this is equal to limit t tending to infinity e power minus at upon minus a plus 1 by a. But now this a is less than 0, therefore this thing will go to infinity, which means that this entire thing will tend to infinity, which means that this xt is not absolutely integrable, and therefore Fourier transform of xt is equal to e power minus at ut for a less than 0 does not exist, and this is by Dirichlet's condition. Okay, please feel free to stop and ask the doubts at any moment of time. Now let us look at the third part of the same question. So it says that my xt is equal to, so this is third part, xt is equal to e power minus at u of minus t, and now this a is greater than 0. So again let's check if it is absolutely integrable or not. So what we will do is we'll consider minus infinity to infinity mod xt dt, which is equal to integral from minus infinity to 0. Since we are having this u of minus t, so it will be from minus infinity to 0, non-zero, else it will be 0, e power minus at dt. This can be written as, so what we will do is we will substitute, let t tilde is equal to minus t, so we have dt tilde is equal to minus dt. So this is simply infinity to 0 minus e power at tilde dt tilde, which is, can be just change the limits with this negative sign. So we have 0 to infinity e power at dt tilde, so it is e power a tilde at tilde into dt tilde. Now we have this a greater than 0, which means that again this integral will tend to infinity, which means that this is not absolutely integrable, and in this case this is not absolutely integrable, and again the Fourier transform does not exist. Okay, now let us look at the last part of the first question. So it says that we have xt is equal to t into e power minus at ut. Now what we can do is we can write this x of t as multiplication of two functions, which is something like this. So we can write this as, this is equal to t into x tilde t, where x tilde t is equal to e power minus at ut. Now let us look at this property. This property here, that is multiplication with time, differentiation in frequency domain. So let us look at this property. So it says that minus jtx of t is having a Fourier transform of dt omega of x of omega. So what we have is the property that we have currently is differentiation in frequency domain, and the property that we have is minus jtxt is equal to d omega of x of omega. So if I shift this minus j to the right hand side, then we have is txt is equal to j times d omega of x of omega, with we can just add a tilde here which won't change anything. And the condition that we are having here right now, the question that we are having here is t into x tilde t. So this is what we are having. Now note, just look at this factor here, that is x tilde t is equal to e power minus at into ut. So this says this function is equal to the function that we had evaluated in the first part of this question, that is here. And we had seen the Fourier transform of this function here, which comes out to be x of omega is equal to 1 upon a plus j omega. So for this x tilde t, this x tilde t is equal to e power minus at ut has Fourier transform x of omega, or let's say x tilde of omega, is equal to 1 upon a plus j omega, and this is from part 1. Therefore xt is equal to t into x tilde t is equal to d omega with and sorry. So this basically what we are having here is x of omega is equal to j times d omega of x tilde omega. So this comes out to be j times d omega of 1 upon a plus j omega. Therefore x of omega is equal to j times minus 1 upon a plus j omega square into j, which can be simplified as 1 upon a plus j omega square, where this j into j results in a minus 1, and therefore this is the Fourier transform of t into x tilde t, or t into e power minus at into ut. So this is the way how we can use the Fourier transform properties if we know the Fourier transform of some standard signals like this exponential signal. So let us go ahead and look at another important signal which is given by this formula here. So let us first try to sketch this signal. So what we have is something like this. Let's say this is my t-axis, this is xt, and let's say what we have been given is the signal is taking a value 1 from minus b to b, and otherwise it is 0. Otherwise it is 0. Okay. Now we need to find the Fourier transform of this signal. This is the signal that we are having and we need to find the Fourier transform of this. So let us do that. So we have x of omega is equal to minus infinity to infinity xt into e power minus j omega t dt. Now this, if I substitute this, it can be observed that it takes non-zero values. It takes non-zero values only for a range of minus b to b. So I can change the limit of these integrals from minus b to b, something like this. So from minus b to b, and in this region it takes the value 1, it is 0 otherwise, into e power minus j omega t dt. Now this I can write as e power minus j omega t upon minus j omega from minus b to b. This is equal to e power minus j omega b minus e power j omega b upon minus j omega. So this I can write as b omega, or let's say 2b omega can write this as 2b into, or let's say 2b upon omega into, inside the bracket, e power j omega b minus e power minus j omega b whole divided by 2j, and this factor, this is simply sine of omega b, and here again we are having a factor of b here. So this entirely reduces to a form of 2b sine of omega b upon omega b, and let's say this is simply sine of sinc of omega b, where the sinc function, sinc of x, is simply sin x upon x. So it is defined as sin x upon x. So this is the Fourier transform of this rectangular function or rectangular pulse, which is non-zero from minus b to b, and it takes a value and it takes 0 from minus infinity to minus b and b to infinity. So this is an important function to analyze, because basically this is how your low pass filter looks. So this is how your low pass filter looks. And that's why it is important for filter based analysis or filter analysis to understand how this function looks in frequency domain. The only change is this nature of your low pass filter is in frequency domain and not in time domain. So by duality, your low pass filter in time domain will look like this sinc function, whereas in frequency domain it will be a rectangular function. We'll look at this duality when in the subsequent questions in greater detail. So with that, let us look at another question. So the next question that we have is this. That is, we are having xt is equal to t into, so this x of t is equal to t into 1, or let's say t, from t ranging from minus 1 to 1, and it is 0 otherwise. So what we are having here is something like this. So this is xt axis, this is t. I have -1 here, -1 here, then -1 here, 1 here. So this is basically 1, and from here to here I am having a straight line and it is 0 otherwise. So this is the signal that we are having. And now we'll try to find out the Fourier transform of this signal. So let's do that. So let us find it by conventional way, that is, let's say x of omega is equal to integral from -infinity to infinity xt into e power minus j omega t dt. This is equal to integral from -infinity to infinity this signal, which is non-zero, from -1 to 1, so I can just simply write it as -1 to 1 t into e power minus j omega t dt, and integration of this is simply minus t into e power minus j omega t upon j omega minus e power minus j omega t upon j omega square from from -1 to 1. Okay, so when I substitute this comes out to be -1 into e power minus j omega t upon j omega minus e power minus j omega t upon j omega square minus e power j omega t upon j omega plus e power minus e power j omega t upon j omega square. So this we can simplify as so I can write this equation as I can combine these terms here, this one and this one. So I can take out -1 upon j omega common. Inside the bracket I have e power minus j omega t. After substituting, this t will vanish because we are substituting t as 1 and -1. E power minus j omega plus e power j omega. Now again I can take these terms here, that is this one and this one. So I can take out 1 upon omega square as common, so plus, let's say, let us take out -1 upon omega square common, and inside the bracket what we have is e power j omega minus e power minus j omega. Let's divide this by a factor of 2 and this by a factor of 2j, and to compensate again we'll multiply and divide by 2j. So this becomes, this 1 upon j is basically minus j, so I can write this as j into 2 by omega, and this factor here is basically cos of omega, and again this factor here is nothing but sine omega. So this is minus 2j upon omega square sine of omega. So this is the Fourier transform of this signal here. Now let us look at the signal that we had in the previous question. So before that, I'll just summarize this as x of omega is equal to 2j common inside the bracket cos omega upon omega minus sin omega upon omega square. Now look at the signal that we had here and compare the signal with this. So for that, let me just add one page. So basically what I'm trying to say is this signal xt, which basically looks something like this. So this xt that we are having is basically minus 1 to 1 and it looks like this. And it is 0 otherwise. Now suppose I take a signal that we had considered in the previous question, which had magnitude 1, and let's say this is my xt, this is, let's say, is my x tilde t, this is also 0 from minus 1 to 1. And now let us consider another signal, or what we basically consider is this which is nothing but t. So basically if I multiply these two signals, I'll get this signal. So basically this xt is equal to t into x tilde t, where this x tilde t is simply the signal that we had considered in the previous question when the value of b is equal to 1. So this is this signal that we had considered from minus 1 to 1 and 1. Okay. So this is basically what we are having. In the previous question, we saw that this signal has a Fourier transform of 2b sinc omega b, or let's say let us look at this, that is 2b sine omega b upon omega b, where now we are having this b equal to 1. So this x tilde omega, or let's say this x tilde t, have Fourier transform x tilde of omega, which is equal to 2b, which is equal to 1 into sine omega upon omega. And we had seen this property previously, that t into x tilde t is simply j times t d omega of x tilde omega. So let us use the same property here. So this x of omega will be equal to j times d omega of x tilde omega, which is equal to j times d omega of 2 times sine omega upon omega, which we can write as 2j, taking 2 common. So we have this 1 by omega as it is. The differentiation of sine is cos omega minus sine omega upon omega square, which is equal to 2j cos omega upon omega minus sine omega upon omega square. And if we compare what we had derived previously, so these two are exactly same. This one and this one are exactly same. Hence we can, since this is a common function and generally it is its Fourier transform is known, so we can simply use the property and just differentiate this function to get the Fourier transform of this signal. Let us look at the next question, that is question 4. So what we are having here is two signals. The first one is this sine omega naught t, and the second one is this cos of omega naught t. and we need to find the Fourier transform of these two signals. So let's start with this sine omega naught t. So we have this xt is equal to sine of omega naught t, and I can write this as 1 upon 2j inside the bracket e power j omega naught t minus e power minus j omega naught t. And by duality property, we know that any constant a has Fourier transform as 2 pi delta a. Therefore, if I multiply this by e power j omega naught t a, then the Fourier transform of this will be simply 2 pi delta times omega minus omega naught. I'm sorry, this is not a, this is omega. Yeah. So this is the Fourier transform that we have here. So if we consider this and apply linearity property, then x of omega is simply 1 upon 2j Fourier transform of e power j omega naught t minus Fourier transform of e power minus j omega naught t. And if we use this property which is defined here, then this e power minus j omega naught t, this e power minus j omega naught t with a equal to 1 basically has Fourier transform of 2 pi del of omega minus omega naught. So this is simply 2j inside the bracket. This is 2 pi delta omega minus omega naught minus 2 pi delta omega. Now here instead of this omega we are having minus omega naught, so it's simply plus omega naught, which comes out to be pi by j inside the bracket delta omega minus omega naught minus delta omega plus omega naught. So this is the Fourier transform of sine of omega naught t. Now let us look at the next part. So what we are having here is xt is equal to cos of omega naught t. Again we'll write it in terms of complex exponential. It actually simplifies many things. So this can be written as e power j omega naught t plus e power minus j omega naught t upon 2. Therefore x of omega is equal to 1 by 2 inside the bracket Fourier transform of e power j omega naught t plus Fourier transform of e power minus j omega naught t. And this reduces to x of omega using the same logic here. So this comes out to be 1 by 2 pi delta omega minus omega naught plus 2 pi delta omega plus omega naught, which is equal to pi delta omega minus omega naught plus delta omega plus omega naught. So these are the these are the Fourier transform of another set of standard functions that are the cosine and sine functions. Okay. So if this is clear, let us look at the next question. So this question says that in the previous question, the sine and cosine signals are periodic. Can you extend the similar idea for finding the Fourier transform of any periodic signal? We had seen in the previous tutorial as well as in the lectures that this Fourier transform is used for aperiodic or non-periodic signals. Now, these sine and cosine functions here, are basically having a Fourier transform, like we found its Fourier transform. but these are periodic functions. So we represented them in some complex exponential form and then tried to find its Fourier transform. So can we extend this similar idea for finding Fourier transform of any periodic signal? So let's try to do that. Now we'll make use of the tool or the frequency domain representation of what is known as the Fourier series. We know that, let's say, this xt is a periodic signal okay, and this xt is a periodic signal, and let's say this xt has Fourier transform as xk, where this xk are the Fourier series coefficients. Okay, and we had seen that this any periodic signal, let's say xt, this xt can be written as summation of, or let's say linear combination of multiple harmonics, or harmonics of its fundamental frequency, that is e power minus j k omega naught t, where this omega naught is equal to 2 pi by t naught, which is equal to fundamental frequency or fundamental angular frequency. And we need to find Fourier transform of this. So this we can write as x of omega is equal to Fourier transform of summation k running from minus infinity to infinity ak e power minus j k omega naught t, which we can write as summation k running from minus infinity to infinity. This xk is constant, so I can take it outside. It is not a function of t, into Fourier transform of e power minus j k omega naught t. I'm extremely sorry, this is plus. This is synthesis equation and not analysis. Fourier transform of e power j k omega naught t, and again we'll use this definition here. So e power j omega naught t will have Fourier transform as 2 pi delta omega minus omega naught. So the Fourier transform, so this Fourier transform of e power j k omega naught t is equal to 2 pi delta omega minus this shift, that is k times omega naught, and therefore this x of omega can be written as summation k running from minus infinity to infinity 2 pi ak into delta omega minus k times omega naught. So any periodic signal with Fourier series coefficients given by ak will have its Fourier transform, which is of the form of summation k running from minus infinity to infinity 2 pi So any periodic signal with Fourier series coefficients AKs will have the Fourier transform as summation k running from minus infinity to infinity 2 pi ak into delta omega k times delta omega minus k times omega naught. So from this example, we can see that this signal, any periodic signal, can have its Fourier transform, which can be found out with the help of its Fourier series coefficients, which is something like this. Okay. If there are any questions for this, please let me know. Let us look at the next question. So the signal xt that is given to us here is xt is equal to e power minus pi t square. So this is basically a Gaussian curve which looks something like this. So this looks something like this, just symmetric about 0 here. This is xt, this is t, and this xt is equal to e power minus pi t square. And we need to find the Fourier transform of this signal which is given here. Now let's see. The Fourier transform x of omega is given as minus infinity to infinity xt into e power minus pi t square dt. I'm sorry, e power minus j omega t dt, and this can be written as integral from minus infinity to infinity e power minus pi t square into e power minus j omega t dt. Now let us consider this. E power minus omega infinity to infinity e power minus pi t square plus j omega pi into t dt. Now consider this factor which we are having here. So we are having t square plus j omega by pi t. Now this is a Gaussian curve here, and we know that if I'm having any function which is of the form 1 upon 2 pi, or let's say 1 upon root 2 pi sigma square e power minus x minus mu square upon 2 sigma square, then integration of this function is equal to 1 from minus infinity to infinity. So if we observe this thing here, it is a square term, whole square term, and we need to bring, or we'll try to bring, a similar term which is present here. So for that we'll have to use the completing square method by adding and subtracting some constants in this equation which is available here. So we'll try to do that now. So for that what we'll do is, first we'll try to get this in the form of a plus b whole square. So this is equal to a square plus 2ab plus b square. So now this is, suppose, my a, so we are having a here, and let's say we multiply this by a factor of 2. So this j omega upon 2 pi is basically your b. So what we can do is we can add plus j omega upon 2 pi square minus j omega upon 2 pi square. Just to compensate, we'll add and subtract. If we do that, then this part here, this factor here is basically t plus j omega upon 2 pi square minus j omega upon 2 pi whole square. Let us substitute this back in this formula which we are having here. So this is equal to 1 upon infinity to infinity e power minus pi t plus j omega upon 2 pi square into e power minus pi. This I can write as minus 1 square. So this minus and minus, okay, I'll just simplify it here further. So this I can write as t plus j omega upon 2 pi whole square minus omega square upon 4 pi square. So here what we'll get is minus pi into omega square upon 4 pi dt. So this pi gets cancelled, and this is a constant which we can take outside. So what we are having is this x of omega is equal to e power minus omega square upon 4 pi integral from minus infinity to infinity e power minus pi t plus j omega upon 2 pi square dt. And one again I'll repeat the same equation here of that Gaussian curve. So basically minus infinity to infinity 1 upon 2 pi sigma square into e power minus x minus mu square upon 2 sigma square is equal to 1, or this I can also write as integral from minus infinity to infinity e power minus x minus mu square upon 2 sigma square dx is equal to under root of 2 pi sigma square. So if I compare it with this, so this 1 upon 2 sigma square is equal to pi, and if so this if I compare this factor here and this factor here, 1 upon 2 sigma square is equal to pi, which means that 2 pi sigma square is equal to 1. So if I substitute this back here, so what I have is this integration will lead to under root of 2 pi into sigma square, which is the sigma square is equal to 1 upon 2 pi into 1 upon 2 pi, which results in 1. Therefore, this x of omega is equal to e power minus omega square upon 4 pi. So if we look at the nature of this function that we are getting here, so this is also a Gaussian function. So we can see that Fourier transform of a Gaussian function is also a Gaussian function. So another, like, let's try to extend this a little bit further. This omega is basically some sort of angular frequency. So this is basically radian per second. So what we can do this, we have this 2 pi f is equal to omega, where this f is frequency in hertz. So if we do that and substitute it back here, this x of f can be obtained as e power minus omega square, that is 2 pi f square divided by 4 pi, and therefore this results in e power minus 4 pi square f square upon 4 pi. This gets cancelled, which is equal to e power minus pi f square. Now just look at this function that we had, this one. So this xt that we had was basically e power minus pi t square, and its Fourier transform, if I consider the hertz frequency, is e power minus pi f square, which is exactly the same function. So this is an important property of Gaussian function, that its Fourier transform is again Gaussian. It has the same form if I consider the frequency in hertz. So you can simply take this e power minus pi f square and substitute this f as omega upon 2 pi and simplify to get back the Fourier transform. So this is an important property for this Gaussian function, and an interesting one also. Any questions at this point? let us look at the next question then. So the next question says that we need to use the properties of Fourier transform. So using the properties of Fourier transform, we need to find the Fourier transform of the signal xt into e power j 4 pi t e power minus a t u t a greater than 0. And the second question that we are having is xt is equal to sine omega naught t into e power minus a t u t, where again this a is greater than 0. So let's try with the first part. Okay, so what we are having is xt is equal to e power j 4 pi t into e power minus a t ut. Now if we look back at the very first question that we had solved, so that was this function here, that is xt is equal to e power minus a t ut, this one, and this function has a Fourier transform as x of omega equal to e power minus x of omega is equal to 1 upon a plus j omega. This we had already solved. Also, while discussing the properties of Fourier transform, we had looked at the property of shift in frequency domain. So e power j t omega naught has a Fourier transform of x of omega minus omega naught. So what do we have is, from previous discussions, what we have is the following two things. The first thing is that this signal e power minus a t ut has a Fourier transform of 1 upon a plus j omega, and this comes from question 1. And the second thing that we have is e power j omega naught t xt has a Fourier transform of x of omega minus omega naught, and this is basically frequency shift property. Okay, so now this we know, the Fourier transform of this is known. So let's say this signal is x tilde t, and let's say this has a Fourier transform of x tilde omega, and this is equal to x tilde omega. Then using this property, using this shift in frequency property, the Fourier transform of this xt, which is x of omega, is equal to x tilde omega minus, here if I compare this, then this omega naught is simply 4 pi, so omega minus 4 pi. Okay, now we have the value of this x tilde of omega as 1 upon a plus j omega. So this I can simplify as 1 upon a plus j times omega minus 4 pi. So this is the Fourier transform of this signal, that is xt equal to e power j 4 pi t into e power minus a t into ut. Any questions at this point?
No, ma'am.
Hello? Yeah, I'm unable to hear you.
Yes, ma'am.
Any questions?
No, ma'am.
Okay, okay, fine. Okay, so let us look at the second part of this question. So here we have xt is equal to sine of omega naught t into e power minus at ut. Now again, this we had seen. So what all things do we have in with us right now are the following. The first one is, let's say, this x tilde t is equal to e power minus at ut. This has a Fourier transform of x tilde omega, which is equal to 1 upon a plus j omega. Second thing that we have from previous discussion is that this sine omega t, the sine of omega naught t, has a Fourier transform as pi by j delta omega minus omega naught minus delta omega plus omega naught. So from this question 4, so this we are getting from question 1. From question 4, sine omega naught t, and let's say this is x hat of t is equal to sine omega naught t, and the Fourier transform of this, let's say x hat of omega, is equal to pi by j delta omega minus omega naught minus delta of omega plus omega naught. This we had seen. And the next thing that we have discussed in the properties is that if I have multiplication of two signals, that is if we are having x tilde t multiplied by x hat of t, then the Fourier transform of this is simply 1 over 2 pi x tilde t convolved with x hat of x tilde omega convolved with x hat of omega. So using these three, we'll try to find what is the Fourier transform of this signal, that is xt equal to sine omega naught t, where the sine omega naught t is simply x hat of omega, x hat of t, and this factor here is x tilde of t. And if we look at the use of this third point which is listed here, so this x of omega, capital X of omega, which is Fourier transform of this xt, is simply 1 upon 2 pi x hat of omega convolved with x tilde of omega. So this we can write as 1 upon 2 pi into x hat of omega, that is pi j, multiplied by delta omega minus omega naught minus delta omega plus omega naught convolved with 1 upon a plus j omega. This gets cancelled, and what we have is 1 upon 2j inside the bracket, this del of omega minus omega naught convolved with 1 upon a plus j omega minus 1 upon 2j delta omega plus omega naught convolved with 1 upon a plus j omega. Now any signal, let's say this x of t, if I convolve with delta t minus t naught, then this is nothing but x of t minus t naught. This delta is basically a delay of t naught. So if I convolve it with a unit delay, it will just convolve with a delay of t naught, then it will just shift that signal xt from its current location by a factor of t naught. So using this property, this factor here can be written as 1 upon 2j multiplied by 1 upon a plus j times omega minus omega naught minus 1 upon 2j to 1 upon a plus j omega plus omega naught, and this is the value of x of omega. Any questions at this point? Okay, if not, then let us look at the 8th question that we are going to see today. So this is a big long question, not difficult one. So it says that I am having a signal xt which is given as sine 2 pi 100t, sine 2 pi 400t, sine 2 pi 600t, and this is passed through a system. This is passed through a system with impulse response ht, which has a Fourier transform h of omega, which is 1 for all the values of omega, such that mod of omega is less than or equal to 900 pi, and it is 0 otherwise. So what we have to do is we have to sketch the Fourier transform of the output, and we need to determine the output, and you also need to find what is the impulse response of this system. Okay, so let us start with this. So first let us look at this xt. So this xt is simply sine of, I can write this as 2 into 100, that is 200 pi t, plus sine of 800 pi t, plus sine of 1200 pi t. And in the previous questions we had seen that this sine of omega naught t has a Fourier transform of pi upon j delta omega minus omega naught minus delta omega plus omega naught. Okay, now if I do use this whatever formula which we had seen in the previous questions and try to find the Fourier transform of this xt, so this x of omega is simply pi by j inside the bracket. Here omega naught is 200 pi, so what we have here is delta omega minus 200 pi minus delta omega plus 200 pi. Similarly, the second factor which is here, this one, has a Fourier transform of pi by j delta omega minus 800 pi minus delta omega plus 800 pi. Similarly, this third factor here, this has a Fourier transform as pi by j delta omega minus 1200 pi plus delta omega plus 1200 pi. So this is the Fourier transform of my input signal. So what do we have is this x of omega. I'll just reiterate the same thing. So it is simply pi by j delta omega minus 200 pi minus delta omega plus 200 pi plus pi by j delta omega minus 800 pi minus delta omega plus 800 pi plus pi by j delta omega minus 1200 pi minus delta omega plus 1200 pi. So this is what we are having here. Now let us try to sketch this. So let's say this is 0 and okay, I'll draw the impulses, respective impulses, and just mention its value or the value it carries at the top of it. So we are having basically impulses which are located at 200 pi, then 800 pi and 1200 pi. Similarly at minus 200 pi, minus 800 pi and minus 1200 pi. Now if we look at this first factor here, so it is omega plus 200 omega minus 200 pi. So this impulse is located here and it takes the value of pi by j. Similarly if we look at this factor here, so it is omega plus 200 pi with a negative sign. So basically it is somewhere here, that is at minus 200 pi, but with magnitude or amplitude or with a scaling of pi by minus pi by j. Similarly we have this delta omega minus 800 pi, so we have another impulse located at 800 pi with value pi by j, and similarly we have another impulse at minus 800 pi with scaling of minus pi by j. Then we have an impulse at 1200 pi, that is here, pi by j, and here that is minus pi by j, and this is omega, and this is simply x of omega. This is what we are having right now. And another thing that we have been given is this h of omega, and it is said that this h of omega takes a value 1 for all the frequencies from minus 900 pi to 900 pi. That is, it's something like this. So this is h of omega, this is omega, takes a value 0 here, 0 here, and this is 1. This is 0. So this is the impulse response that we have right now. And if we look at the convolution property, so basically what we have this, yeah, so what we have is this y of t, that is output of the system, is xt convolved with impulse response ht, which implies that y of omega is simply x of omega multiplied by h of omega. So basically this y of omega will be multiplication of these two functions here. So let us try to do that. So this is x of omega that we are having, and I'll again just superimpose the thing that we are having here, like h of omega in the same diagram. So let's say this is my 900 pi, this is 900 pi, this is minus 900 pi, and this is 900 pi, and the filter that we are having has a response something like this. And this is the value 1. So if we observe here, this last frequency, this is not passed through the filter. That is, these last frequencies, that is at minus 1200 pi and 1200 pi, are simply ignored or rejected by this filter or by this system. And it is only allowing the components that are located at this minus 800 pi, minus 200 pi, 200 pi, and 800 pi. So if we do that, that is if after multiplication, so basically this is h of omega. So the y of omega will be something like this. That is, this frequency and this frequency will be rejected, and these components which are located at these 4 places will remain as it is, because the amplitude of this filter is simply 1, and therefore this is y of omega that we are having here. Now if this is y of omega, so this y of omega is simply pi by j. So this y of omega is simply pi by j multiplied by delta omega minus 200 pi minus delta omega plus 200 pi plus pi by j times delta omega minus 800 pi minus delta omega plus 800 pi. So this is what we are having. Now look at this factor here. This factor here is simply Fourier transform of sine of 200 pi t, and the factor which is present here is simply Fourier transform of sine of 800 pi t, and therefore y of t is simply sine of 200 pi t plus sine of 800 pi t. So this is the Fourier transform of this output signal, and this is the output of the system that we have been given. Now what do we actually understand from this question is, like, this signal xt is a bit complicated, and we don't know how this filter will be looking in time domain. So let us first try to look at how it will be looking in time domain. So what we are having is this h of omega is something like this. From minus 900 pi to 900 pi. Yeah, this is h of omega, and from inverse Fourier transform definition, this ht is equal to 1 upon 2 pi integral minus infinity to infinity h of omega e power j omega t d omega. This can be written as 1 upon 2 pi. It is non-zero only between minus 900 pi to 900 pi. So this can be written as integral from 900 pi to 900 pi. In this it is 1 into e power j omega t d omega. This can be written as 1 over 2 pi e power j omega t upon gt from minus 900 pi to 900 pi. This is equal to 1 by pi into e power j 900 pi t minus e power minus j 900 pi t upon 2j. So this is equal to 1 upon pi t. This factor here is simply sine of 900 pi t. So this ht, that is impulse response ht, is equal to sine of 900 pi t upon pi t. Now when we are using this LTI system, so what basically we are having is this y of t is equal to xt convolved with ht. Now look at this signal that we have been given. This is summation of three sine functions, and again this ht is again a complicated function which is somewhat a sinc function. Now if that is the case, then in that situation this convolution operation that is available here, this convolution is complicated. But if we treat the same question in frequency domain, it is simply multiplication of this x of omega, that is frequency or Fourier transform of the inputs is that is xt, and the Fourier transform of this of the impulse response of the system, that is this h of omega, which results in this thing. And this using this representation we can take the inverse Fourier transform and get this output. Now in any time using this multiplication is way much simpler than considering the convolution operation. So that's why this approach sometimes helps a lot in finding the output of any system, similar to the Laplace transform. So this kind of representation helps. This kind of representation helps a lot when we need to design some filters. For example, if I know that I don't want a certain number, a certain frequency components, that is, suppose I'm talking and there is some noise coming out, and let's say I know that this noise will be available at some higher frequencies. So what I can do is I can just pass the frequencies which are in the range of my voice. That is, suppose this is the range of frequency that I actually want in my signal, which I need to transmit or just process afterwards, and these are the frequencies that I don't want, so I can just reject those by designing appropriate filters. And this visualization of what kind of frequencies I want, what I don't need, can be better interpreted when I go to frequency domain compared to the time domain interpretation. This you can't understand from this. Here is just a sign, so you can observe which frequencies are present, but it may happen that there is some complicated function, like my voice is not a voice is a signal which I can't represent mathematically. So in that situation it's very difficult to understand which frequencies are present and which are not, which frequencies are unnecessarily dominating my signal which I don't want, and I can just suppress them. So these kind of visualizations help a lot when we go to frequency domain or we take the Fourier transform. Any questions at this point?
No, ma'am.
Okay. So let us look at the ninth question. So this question actually has two parts. So what it is given is, consider an RC circuit with input as a source voltage and output taken across the capacitor. So what we are having is this circuit here. So this is my resistor R, this is capacitor, and this is the input voltage that I am giving, and this is, let's say, XT, and I am taking the output at YT, and it is across capacitor, this is C. It is given that this C is 1 microfarad and this R is 10 kilo ohm. So this C is 1 microfarad and this R is 10 kilo ohm. And we need to find what is the 3 dB frequency for this signal. So basically this example was actually taken in the lecture, so I'm not going to repeat it, but I'll repeat the entire derivation, but I'll just repeat the system response, that is this h of omega, which came out to be 1 upon 1 plus j rc omega. Let's say I write it properly, j omega rc, and we had seen that this magnitude response, or let's say this mod h omega square is equal to 1 upon 1 plus omega square r square c square. This was seen, and it was also seen that this magnitude response actually looks something like this. That is, it is passing the lower frequencies and it tends to 0 as this omega tends to infinity. So this is, let's say, my mod of h of omega. This is omega axis, and the 3 dB point was also derived. So let's say this is 1 by 2, then this is omega 3 dB. So this omega 3 dB was obtained as 1 by RC, which for given values comes out to be 1 upon R, that is 10 kilohertz, 10 kilo ohm, that is 10 into 10 power 3, multiplied by C is 1 microfarad. So 1 into 10 power minus 6, which comes out to be 100, which is equal to 0.1. Let's just keep it as 1 by 100, 100, and this is radians per second. So this is the 3 dB frequency for this signal, which was considered in the lecture, in the normal lectures. But now the next part is, what will happen if this output is measured across the resistor? Now, how does this circuit change now? So we have, let's say, a capacitor here and a resistor here, and now this was my xt, input is same, and now my output is taken across this resistor, which is resistor voltage. Let's say this is R and this is C. What will change, or what will happen to the output, or what will happen to basically the system response if I measure the output across this resistor? So for that, let's say I have a current IT flowing through this. So first thing that I know is, by Ohm's law, this YT is equal to I into this R into IT. Second thing that I know is, this IT is C d dt of VCT, which means that the voltage across this capacitor VCT, so this is VCT, which is voltage across capacitor, can be simply written as 1 by C integral from minus infinity to T I T dt. So this is what we are having here. Okay, and therefore, and we from this equation, this IT is simply YT by R. Therefore, this VCT is equal to 1 by RC integral from minus infinity to T I of tau. Let's say be precise in writing this. So this is I tau d tau. So by substituting I as YT by R, what we have is YT, Y of tau d tau. Okay, now if we consider the voltage law, so we have XT is equal to VCT plus YT, which I can write as 1 by RC integral minus infinity to T Y of tau d tau plus YT. Now if I differentiate it, this comes out to be d dt of xt, which is equal to 1 by RC YT plus d dt of YT. So what we are having is d dt of xt is equal to 1 by RC y of t plus y of t d dt of yt. Now if we consider the differentiation in time property, that is if x of t has Fourier transform x of omega, then d dt of xt will have Fourier transform of j omega x of omega. Similarly, d dt of yt will have Fourier transform of j omega y of omega. So using this will have a Fourier transform of j omega x of omega plus 1 by RC y of omega plus j omega y of omega. Now this can be written as j omega x of omega is equal to 1 by RC plus j omega y of omega. Therefore, y of omega upon x of omega comes out to be j omega upon 1 by RC plus j omega, which is equal to j omega RC upon 1 plus j omega RC. So what we are having is y of omega upon x of omega, which is equal to h of omega, which is system transfer function, and it comes out to be j omega RC upon 1 plus j omega RC, and this is equal to, and this implies that if I consider magnitude of h of omega square, this comes out to be omega square r square c square upon 1 plus omega square r square c square. Now consider this case. So if I have omega equal to 0, which implies that magnitude of h of 0 is equal to 0, and let's say this omega tends to infinity, this implies that this factor, this magnitude of h of omega square will tend to 1. If this is infinity, these two will get just cancelled out and I'll have 1. So if I draw this, This is my omega axis. This is, let's say, magnitude of h of omega, let's say square. So at 0 it is 0 and it will extend to in 1 as this value tends to infinity. Similarly, this thing is valid even for minus infinity as well, because it is omega square, so it will tend to 1. So again, this will also be something like this. Now basically this is allowing high frequencies to pass, and this is an example of high pass filters. The basic, very basic example of high pass filter, and this was allowing the lower frequencies, and therefore this was an example of low pass filter. Very basic low pass filter. So this is what we are having here. And now the other thing that we need to find out is what is its 3 dB frequency. So at omega 3 dB, this magnitude h of omega 3 dB square is equal to 1 by 2, which is equal to omega 3 dB square r square c square upon 1 plus omega 3 dB square r square c square, which after simplification what we have is 2 times omega 3 dB square r square c square is equal to 1 plus omega 3 dB square r square c square. Therefore omega 3 dB square is equal to again 1 upon r square c square. Therefore omega 3 dB is equal to 1 by rc. This we had found out as 100 radians per second. Any doubt in this question?
No, ma'am.
Okay. So let us look at the last question, and what we have here is we have been given a signal xt is equal to sinc of bt, and let's say this sinc is defined as sin x by x. Now for solving this, let us go to this question which we had seen very initially. It is this question, that is, if I am having a signal which looks something like this, then the Fourier transform of this is this signal, that is 2b sinc of omega p. So what we have is what we had seen earlier is my x of t, if x of t let's say this is x tilde t is of the form this, so Fourier transform of this was b times sinc p omega. Okay, so what we can write is the sinc this x tilde t by b has a Fourier transform of sinc b omega. Now what we have been given is xt is equal to sinc bt. Now we'll make use of duality property. Then in that case, this sinc pt will have a Fourier transform as 2 pi into Fourier transform of x tilde of, or let's say this, sorry, 2 pi into x tilde of minus omega by b. This is using the duality property. So what does this duality property say? If x of t has a Fourier transform as capital X of t, then capital capital X of omega, then this capital X of t will have Fourier transform as 2 pi small x of minus omega. So this is what we are having here. So this is equal to 2 pi x tilde minus omega by b. I'm sorry, this is 2b. This is 2b, and therefore this is pi by b. Now if I flip this signal, about this x of t, x tilde t axis, it will remain same. So therefore this x of omega will be the same function which is non-zero from minus infinity to minus b and takes a value of pi by b from minus b to b, and this is the value of x of omega. So this x of omega is equal to pi by b x tilde of minus omega. Any doubts at this part? Okay. So this was all what I wanted to cover today. So if you have any questions, please let me know. Otherwise, you're free to leave the meeting.
One doubt in Gaussian function.
Hello?
A doubt
Gaussian.
in Gaussian function problem.
Okay, Gaussian function problem. You want me to solve it again?
Oh, no, ma'am. One doubt.
Okay, what doubt do you have here?
Ma'am, that it is minus infinity to infinity that the that property is standard.
This one? This property?
Yes, ma'am.
Yeah, this is actually a standard property. Actually, if you look at the random variable stuff, so there is one Gaussian random variable which has the probability density function as like this, and if you integrate the probability density function, it leads to value 1. So this is a standard property.
Okay, ma'am.
Yeah. So you can actually take this as it is for reference. Maybe integrating this may lead to some complications and some difficult stuff. So or you may just do one thing. You do this, try to integrate minus infinity to infinity e power minus x square by 2 dx. This should give you root 2 pi. You just try to solve this. This will include some gamma function, or let me
Okay.
do it. At the end, I'll just do it. Yeah, yeah, okay. So what we have is, yeah, okay. So let's say I have this integration from minus infinity to infinity, e power minus x square by 2 dt. This I can write as 2 times, it is an even function, 2 times integral from 0 to infinity e power minus x square by 2 dt. I hope this is okay. Then what I can do is I can write this x square by 2 dt, x square by 2, and this is not dt, this is dx, x square by 2 equal to t. So this is 2x by 2, so it is x dx is equal to dt. So this is dx equal to dt by x, and here from here my x comes out to be under root 2t, right? So I can write this as dt upon 2t, under root of 2t. Okay, so this integral changes 2 times integral 0 to infinity e power minus t into 1 upon root 2t dt. So this is root 2 integral 0 to infinity e power minus t power minus 1 by 2 dt, which is equal to root 2 integral 0 to infinity e power minus t into t to the power 1 by 2 minus 1 dt. So actually this is of the form integral 0 to infinity e power minus t power alpha minus 1 dt, and this is equal to gamma of alpha. So this entire integration reduces to root 2 into gamma of 1 by 2, and this results in this gamma of 1 by 2 is basically equal to root pi. This is standard values, so this reduces to 2 pi. Is it okay? So
Yes,
by
ma'am.
making use of this property, even if I make some shift of minus a or any shift, this integral won't change. This is a standard thing. Okay,
Okay, ma'am.
yeah. So this is all that I wanted to cover today. So if there are no further questions, you may leave the meeting. Thank you.
Thank you.